Hi everyone, my name is Mudawat Lakshman of third semester CSE F section. So today I am going to discuss about the bivariate normal distribution in the subject probability and statistics. So let's dive into the introduction part of the bivariate normal distribution. The bivariate normal distribution is a two variable extension of the unvariate normal distribution that describes of the joint behavior of two continuous random variables that are jointly normally distributed. The distribution is widely used in statistics, finance and engineering to model correlated data. The bivariate, so here the introduction part is saying that the bivariate normal distribution is an important extension of the familiar unvariate normal distribution. But here it deals with two variables instead of one. Essentially, it describes the joint behavior of two continuous random variables that follow a normal distribution simultaneously. What makes this special is that it not only captures the individual distributions for each variable but also correlation between them. This distribution is widely used in statistics, finance, engineering, and social sciences, particularly when two variables are related in some way. For example, the joint modeling of height and weight or the correlation between stock market returns of two companies. So this is all about the bivariate normal distribution. Next, dive into the definition and key properties of bivariate normal distribution. The bivariate normal distribution is characterized by a mean vector and a covariance matrix. Its probability density function, like we call it PDF in a small, is a smooth bell-shaped surface in two dimensions. The distribution is symmetric around the mean vector and exhibit elliptical counter of equal probability density. Here, the definition itself is saying that the bivariate normal distribution is a mathematically defining using two components, a mean vector and another one is matrix, which represents mean vector, which represents the average values of two variables, and a covariance matrix, which captures their spread and correlation. Its probability density function PDF forms a smooth bell-shaped surface in the two dimensions, unlike the unvariate normal curve. Here the equal probability regions appears as ellipses centered around the mean. The key properties include the means of two variables are mu x and mu y. Their standards derivations are omega x and omega y and correlation coefficient p, which determines how strongly and its directions the two variables are related. Now, what is the mathematical formulation of these bivariated numbers are? Let's dive into the key points, key properties of these two variables. Like we can take x and y means mu x and mu y by mu x and mu y. So that's the thing. Standard deviations are sigma x and sigma y. So correlation coefficients are rho. So we can say mathematical formulations here. Just yeah. What is a mathematical formulation? Mathematically, the joint probability density function of bivariate normal distribution involves parameter for the means, variance and correlation coefficient. The formula includes an exponential function with a quadratic form of the two variable x and y. An important requirement here is that a covariance matrix must be positive definitely, okay? Meaning it produces valid probability values. This mathematical structure allows the model to capture both the spread of each variable and the independence in precise way. And next, we'll dive into the parameters of the distribution. Parameters of the distribution. So, the distribution is defined by four parameters. There is mu x, mu y, and the variance is sigma x power 2 and sigma y power 2. The correlation coefficient rho means the linear relationship between two variables. These parameters influence the shape, orientation, and spread of the distributions counter. Here, the parameters of the distributions are the bivariate normal distribution is fully defined by four main parameters. Those are mu x, mu y, that which sets the central point of the distribution. The variances are sigma x power 2 and sigma y power 2, which describes the spread along each axis, and the correlation coefficient is rho, which measures the strength and the direction of the linear relationship between two variables. A positive correlation indicates that as one variable increases, the other tends to increase, while a negative correlation indicates the opposite. Together, these parameters determine the shape, size, and orientation of the probability counters. Next, we dive into the counter and shape of the distribution. The counter of the bivariate normal distributions are ellipses centered at the mean vector. We know that, and the orientation of the ellipses depends on the correlation coefficient, that is rho. Okay, when rho equal to 0, the distributions counter are aligned with the axis indicating independences. Okay, the shape of the bivariate normal distribution is best understood through its counters, curved lines that connect points with equal probability density. These counters from ellipses centered around the mean vector. The orientation and tilt of these ellipses depends on the correlation coefficient ρ, where ρ equal to 0, the ellipses aligned with the coordinate axis, meaning the two variables are independent. When ρ is not equal to 0, the ellipses tilt, reflect the strength and the direction of the correlation. This visualization gives a clear picture of how the variables are related. Next, we'll dive into the marginal and coordinational distributions here. So we got the marginal distributions of each variable are unvariate normal distribution. Conditional distributions of one variable given other are also normally distributed. These properties simplify analysis and inference and multivariate data. Going to deep this thing, one of the most useful properties of the bivariate normal distribution is marginal distributions. That is, the distribution of each variable separately are themselves normally distributions. Similarly, the coordinational distribution of one variable given the other is also normally distributed. This property makes it particularly easy to analyze subsets of data, as we can confidently apply unvariant normal methods within these two variable framework. Next, we'll dive into what are the applications of these bivariate normal distributions. Let's dive into deep here. It is used in modeling correlated finances returns and risk assessments. In engineering, we use it like it helps analyze measurement errors and signal processing. In social sciences, it models relationship between paid measurements like height and weight and all. So this distribution finds wide applications across multiple fields. In finance, it is used to model correlated returns of assets, helping portfolio risk assessments. In engineering, it helps analyzing measurement errors like noise in signals and reliability problems and all. In the social sciences, it can model natural relationships such as height, weight, income, expenditure, test scores, and two subjects and all. Essentially, whenever two variables are related and approximately normal, the bivariate normal distribution provides a robust framework for visualization, for analysis. Next, we'll dive into the visualization and interpretation of these bivariate normal distribution. So, visualization plays a big role in understanding the bivariate normal distribution. Typically, it represented either as a 3D bell-shaped surface plot or 2D counter plot of ellipse. The ellipses indicates each equal probability regions and show the strength of correlation. Narrow tilted ellipses indicates a stronger correlation, while nearly circular ellipses indicates weak or no correlation there. Interpreting these visuals gives us direct insights into the relationship between the two variables, making it easier to understand the real world data behavior. And let's dive into the limitations and assumptions of these bivariate normal distribution here. So the distribution assumes linear relationships and joint normality, which may not hold in all data. Outliers and non-normal marginal distributions can distort analysis based on this model. Care must be taken to validate the assumptions before applying the bivariate normal model. Here, despite its usefulness, the bivariate normal distribution comes with a certain assumptions and limitations. It assumes that the relationship between the variables is linear and that both variables follow a joint normal distribution. However, in real world data, this is not always the case. Outliers, skewed data, or non-linear relationship may cause deviations and all. If these assumptions are violated, the conclusions drawn may be misleading. These before applying this model. One must validate whether the data truly fits the assumption of normality and linearity. References. So have referred these things from internet and from a book of Johnson, Ellen, Coates, Balakrishna for on continuous on unvariated distributions, and I have taken this information from academics and some of from library and all. So let's dive into the conclusion here. So the bivariate normal distribution is a powerful statistical model that extends a familiar normal distribution to two variables. It not only captures the behavior of each variable individually but also explains how they are related through correlation. The distribution mathematically elegance lies in a mean vector, covariance matrix and correlation coefficient, which together defines it's a bell-shaped elliptical structure. So this is all about the bivariate normal distribution. So I'm done with bivariate normal distribution. Thank you.